So you're good to go? No questions? All right. We're in the final section of chapter 4. It's Bayes' theorem or Bayes' formula. If you look in your book, it'll get to 4.8 section, that'll say CD-ROM. I don't know why they didn't bother to publish what they have in the CD-ROM, but there's a chapter of the text under CD-ROM. I've also put that out on Angel as a PDF file, and I'll have my notes to go by. The general topic is Bayes' theorem, or Bayes' formula, and it's based on conditional probability, which we've been working with, and it's a little bit of a twist of how we've been viewing things so far. Now, the truth is, we're barely scratching the surface of Bayesian statistics or probability. I mean, really barely. It's a whole huge field out there, and for a long time it's pretty controversial. But it's been used a lot in the last half of the century. Are you familiar maybe with World War II, Turing and the Enigma machine? They broke the code, used Bayesian statistics and probability. And it's becoming more prominent. But again, I'll say we're barely going to scratch the surface of it. And it all starts with the simple formula that we went over earlier. We took the rule for a probability of an event in two trials, and we did a little bit of algebra, and we came up with a formula for a conditional probability. And I'd read that, the probability of B given A. Remember, the event to the left of the vertical line is what I'm interested in. To the right of it, it's information I already know. And as long as P of A, that probability is not zero, then I can use this formula to find that conditional probability. All right, some examples to get your mind set for Bayesian probabilities. Let's suppose the event we're interested on, event B, is VMI is going to win the football game. All right, with no other information, you come up with a probability P of B, probability of winning. If you have additional information, you can come up, you can improve that a priori probability with additional information. For example, if you know the opponent is Rockridge County High School, then we'd say the probability now that VMI would win is the probability B given AC1. Right? We've been thinking like this. If you're playing the Washington Redskins, you'd probably adjust your probability again, given that information, and you'd say it's different. So keep in mind, we have probabilities before and after we have information, and as we get additional information, we revise our probabilities. And that, in a nutshell, is a very simple explanation of what Bayesian probabilities are all about. We update probabilities based on what we learn. So let's turn this example around now. Suppose you know that VMI won the game, but you don't know who they played. Now we might ask questions, well, what's the probability that they play local high school given that they won? Or what's the probability that they play Redskins given that they won? At different points in time, I have different information, and I can use that to update my probabilities. And so in Bayesian, what we're often doing is updating a prior probability with a posterior probability. All right, it's kind of fancy language, but it makes sense. Prior probability is that's what I know as of now. Posterior probability means I get more information, so I update my prior probability, and the way I update it is using a formula, Bayes' formula. That's pretty obvious, isn't it? Don't panic, don't worry about it. That's one form of the formula. That's actually one of the easier forms of the formula. You can go out to math sites and it's about twice as long as that. Here's what's important to us. Well, I guess what's really important to you is that that's on your formula sheet, so you don't have to memorize it. Right? So that's really important. What's important to us is to understand what the pieces are. P of A is my prior probability. That's what I know now. And this formula is a way of combining other information after the fact to get a posterior probability. That's Bayes from the view about 30,000 feet. That's fine for us right now. Okay? Let's take an example. And I'm going to use the example that's in your book, or actually in the CD-ROM, has this PDF file. So here's the situation. We know in this particular county, 51% of the population are males, 49 are female. And a person is selected at random. What would be the probability that person is a male? Van Dynen? This is not a trick question.
No. So it'd be 51 over 100?
Yeah, 0.51. That's not a conditional, that's a straightforward frequency rule, 51%, 0.51. All right, so that's your prior probability. Let's suppose a scenario that all these people are in the auditorium, one of them's selected, you don't observe it. They're behind a curtain on the stage, and now, what's the probability that person is a male or female? Well, if you know nothing else, then the probability that person's a male is 0.51. All right, but you know something else. From behind the curtain, you smell cigar smoke. You have extra information. Can you update your probability now that that person's a male or female? You can if you have some additional information. What we need to know is if 9.5% of males smoke cigars and only 1.7% of females smoke cigars. And we'll use those two pieces of information to update our probability now that I smell cigar smoke, you update that probability that person's a male. And as your intuition would say, it's going to go up, isn't it? But what will it be? We can calculate that. Let's use our typical nomenclature for events. I have M a male, complement of male, complement of M a not male or a female, cigar smoker, not a cigar smoker. And what do I know? Well, I know that probability of a male is 0.51. But I know more than that, too. Someone tell me in English what that probability means, P of C given M.
The probability of event C happening after the event M.
Event M. So translating to our C's and M's, it would be?
The probability that the person is a cigar smoker after you found out that he was a man.
Excellent. That's exactly what it means. And we've been told that's 9.5% or 0.095, right? That 0.095 is the probability that a person smokes a cigar if you know that person's a male. Okay? That's an important skill. Translate that English into the symbols here. All right, someone translate that second, that bottom probability for me into an English sentence. How would I say that?
Probability that someone smoking a cigar and they're a female.
Yeah. So given that this person is a female, what's the probability that she will smoke a cigar? Well, you're told that. We're told 1.7% of females smoke cigars. So that's that probability. Now I claim I've got all the numbers I need to plug it into Bayes' formula. You can trust me on this, don't try to write down all the notes. It's up there on the PowerPoint Angel. But if you plug those in to the formula, you get 0.853. So our probability that that person is a male has gone from 0.51 to 0.853, our posterior probability. We got extra information, we update our probability. All right? Makes sense, doesn't it? Of course it makes sense. It's math. Now, you can use the Bayes formula at any time. That's always available to you, and you have a formula sheet. Today I'm going to show you another way to calculate it that I think is a little bit easier. Then Monday we'll do actually two other ways to calculate it. These conditional probabilities are really important, and they come up a lot out there in the real world. So let's take this information and create a contingency table. We're familiar with those, and we like those. It's really easy to calculate probabilities with a contingency table. And my table is going to look like, let's see what my table is going to look like. So I'll have males and females, cigar smokers, and non-cigar smokers. And we call it a contingency table. I have numbers here to represent the counts from my sample that meet these criteria. So in here in this cell would be the number that smoke cigars and that were male. In this cell it corresponds to the number of females that smoke cigars. And in this cell, the number of males that don't smoke cigars, and so on. Okay? Contingency table is just taking our population, in this case, putting it in 4 different distinct categories. Let's use that information we're given to manufacture a contingency table. We can make one up, as long as we don't cheat and we keep the probabilities the same. So for example, I'm going to say, just to make the math nice, let's suppose we had 100,000 people. What would I put in this cell right here? The very first piece of information, 51,000. And where did you get that? Well, 51% of the population is male. So that's easy, then that means I can fill in this, that's 49,000. 49,000. Okay, our goal here is to fill in all these cells, and then we can use the contingency tables just like we did earlier. It becomes very easy to answer the questions. How can I use this fact? 9.5% of males smoke cigars. Yeah, this row is the row that corresponds to males. So out of my imaginary population of 100,000, there would be 51,000 males, and how many of them would smoke cigars? Yeah, 4, 8, 4, 5. All right, what's the other piece of information I have? Well, I know that 1.7% of females smoke cigars. Well, my imaginary population, 49,000 females, 1.7% of them would be 833. Now, it's not hard to figure out then. I've got missing cells, 1, 2, 3, 4, but I can easily calculate those, can't I? Because this plus this has to equal 51,000. This plus this is 49,000. I add those up and get the bottom rows. So with just a little bit of work, I've now created a contingency table, and I hope I've convinced you that's equivalent to those probabilities I had to begin with. And there's nothing magic about 100,000. I could have used 1,000,000. I could use 10, 47. It doesn't matter. Since I'm using percentages, it's really the proportional relationships between the cells that's important, not the actual values themselves. Okay, well, we know how to calculate probabilities with these guys, don't we? The probability of M given C, the probability that the person's a male, given that I detected cigar smoking. Well, I concentrate on my first column, wouldn't I? Remember, using the contingency tables, what I'm given is what I pay attention to, and I ignore the rest. Well, if I'm given that the person smokes cigars, that's all I'm dealing with. Those 5,678 people that smoke cigars. Now, of those, How many are male? 4,845. That's the same probability as I got before using the base formula. I think it's a little bit easier. You can use either one, and actually, if you dig into the math, you'll see that what I just did here with my hands waving them around, going to that column, and then deleting the other column and going to that cell, I actually did a Bayes formula kind of verbally with my hands. It's the same thing. But I think it's a lot easier to see it in the table. All right. Let's do another one. And this one is interesting because it comes up in the real world. Actually, I hope you're never faced with this. But I've read articles that our medical profession aren't always very good at using probabilities. So if you go to your doctor, hopefully many years from now, and you have a test, and he says, "Steuben, I got bad news for you. It's positive. And the test is 98% accurate." So should he write his will, say goodbye to all of us, back to VMI and see his old professors? Probably not. Actually, we'll see here, the probability that he actually has cancer might be very, very low, even though the test is 98% accurate. How can that be? Well, let's do the numbers, let's do the math. I need to know some more information. But first, let's understand this number, 98% accurate. And we need to get our symbols and our events here. So I'll say C is the event you have cancer, N is the event you don't, plus is the event that the test indicated cancer, and minus is the event that the test did not indicate cancer. That first sentence, translate that into a probability expression for me. How would we write that given these events? Go for it.
Is it probability of cancer given that the test is positive?
It's exactly that. It's not. Now, what you're more interested in. No, actually, I'm sorry. I got that backwards. It's not that. How would they test a test for cancer? How would you know it was accurate or not?
Person actually had cancer.
Yeah, you have to.
Yeah. You'd have to get a group of people that were known to have the type of cancer that you're screening for, give them that test and see how often you detected cancer. So when it says the test is 98% accurate, what they mean is if a person has cancer, that's the given, then the probability that this test will detect it is 98%. That's the probability that they're giving you. Now, you as a human being, what probability are you interested in? You're interested in this one, right? You're much more concerned about, now wait a minute, the test is positive. Do I have cancer? They're different. Okay. Let's look at those other ones. That's 7%. What is that? How would I write that in probability terminology? 7% of the cases that tested positive. In 7% of the cases that test positive, the patient does not have cancer. When the patient does not have cancer, 7% test positive. So that would be a false positive. So how would I write that using my events? What's given? That case?
You've got a plus on the right,
Yeah.
and then,
We're using N for not cancer. Yeah. So that's a false positive. And and that is equal to 0.07. And the last thing we know, the probability of getting this cancer in the general population is about 1 in 10,000. So that's probably the PSC equals 0.00, tens, hundreds, thousands, 10,000s. Tens, hundreds, thousands, 10,000. All right. Let's do the numbers. The first thing we're going to do is we're going to construct this contingency table. And again, I pick a number here that's convenient. I picked 100,000. Why not? So if one person in 10,000 gets this cancer, how many in 100,000 would have it? Well, 10 then. And how many wouldn't? 99,990. All right? First column's done. Now I'm using my next clue. A diagnostic test correctly detects the disease 98% of the time. Okay, where's the cell or row that corresponds to the people that have had cancer? This is right here. So 98% of the time, I'll get a correct positive test result. So 98% of 10 is 9.8. Now, don't be disturbed by getting decimals here. That's fine. We're not really dealing with real people here. We're just setting up numbers that are in the same proportion as the probabilities we've been given. That's 0.98, that's 0.02. The next piece, yes?
Sir, isn't 9.8 0.02 wrong? Because together that many
Oh, 0.2. 0.2. I did that. Thank you. I go over these so carefully too.
So is that the same, the second one should be 92,990.
Oh man, gotta do this on Paris weekend too. Yeah, I think all right. I goofed out.
We'll let it slide.
You'll let it slide? Give me some slack?
Yeah.
See, I don't give you slack, do I?
10 minutes early.
I know what I did now. I changed the problem. I started cutting and pasting again. I should have done that. And then we can fill in the rest of the totals. All right, so they're going to be off a little bit here. Apologize. I'll update Angel. Now we're ready to calculate the probability, aren't we? What are we interested in? The probability of C given a plus. If the test is positive, how likely is it that I got cancer? All right. We know how to use that table. What goes in the denominator? How many of these, out of 100,000, how many would be positive? Yeah. Of those positive, how many actually have cancer? 9.8. So you've got calculators. What's that number? It's a small number. 0.0014. Less than 1/10%. How can that be? Did I make another mistake? Hope I didn't. How can that be? The test is 98% accurate. But yet, if you got a positive test result, it's unlikely that you have cancer. What's going on here? Who can see what's going on? There's nothing up my sleeve. 100,000 people. What's this number represent again? But a positive test result. So what would you call that? False positive. It only happens 7% of the time. Doesn't sound like much. But the cancer is so rare. Cancer only happens 1 in 10,000. So most of the positives are false positives. It's that 7% of all of these people who don't have cancer that are getting positive results incorrectly. And the very few that do have cancer, yeah, we'll get most of those, we'll detect those, but compared to all the false positives, it's very small. So the reality is, in this case, because the cancer is rare and the test gives a lot of false positives, a lot of people are going to get pretty depressed for not a good reason. And from what I read a little bit in the literature, that actually, this is an issue out there in the medical world. Correctly conveying information to patients. And in this example, I've been updating it. I won't take you through it now, but the subsequent ones, you can see what happens if the cancer is less rare, then there's fewer proportionally false positives. So then if you get a positive, your probability goes up. Or if the test has fewer false positives, instead from 7% it goes to 1%. That means if you got a positive, then it'd be more likely that you had cancer. But in this description we have here, the reality is not very likely at all. Okay? You can see you're all stuck. All right. Well, since this is Parents' Weekend, I have a treat for you. And you're special. I didn't get to do this with my earlier class. But since we have some parents here, might be able to resonate with this. How many have ever watched the Monty Hall program? Yes, yes. All right, when I ask the question, give your truthful answer, all right? I'll have to explain it for this other generation here. Those important peaks, pinnacles of Western culture. It's a game show, and you can tell by his wonderful attire, he was back in the And at the end of the show, Monty Hall would take the contestant up to the stage, and there would be 3 doors, 3 curtains, whatever. Behind one of them was a great prize. Fancy car or vacation or jewelry, wonderful stuff. Behind the other 2 doors was junk, which we symbolize with goats. Right? So if you're lucky, you win a car. If you're not lucky, you get a goat. Now, pretty straightforward probability. What's the chance I'll get the car on my first guess? 1/3. But Monty doesn't stop there. You pick a door. Then Monty opens another door, but that door will have a goat behind it. He knows which doors to pick. And then he asks you, do you want to stick with your door or do you want to switch? Which should you do? Or does it make a difference? Should you always stick with your door? Should you always switch? Or does it not make a difference, 50-50? Right, think about that a minute. I'm going to ask you which you think it is. So call it stay, switch, 50-50. In other words, it doesn't matter. Has everyone made up their mind? How many would say stay? Stay where you are. 1, 2, 3, 4, 5, 6. How many would always switch? 1, 2, 3, 4, 5, 6, 7. How many say, don't waste my, it's 50-50? 1, 2, 3, 4, 5, 6. I'm not sure if my numbers add up here. I think I'm a little short, but we'll go with that. All right, I saw a smile in the back row. What's the answer? Switch. Switch. You played a lot? But you've seen this. All right. The best explanation I've seen of the Monty-Hall problem is this guy right here. And plus he's got a great English accent.
Hello everyone. Today I'm going to do a modern classic for you, or to put it another way, a modern cliche, which is why I want to get it out of the way. Today we're going to do the Monty-Hall problem. The Monty-Hall problem. Now the Monty-Hall problem is very famous these days. The idea is this: we're on a game show, and I'm your game show host. So you're going to have to imagine the sparkling jacket, and we've got 3 doors. Now behind one of these doors is a car. Behind each of the other 2 doors is a booby prize, which for some strange, inexplicable reason is a goat. Now our budget doesn't stretch to a car and 2 live goats, so we're going to have to play for something else. We're going to have to play for this mogwai. So that's what we're playing for today. We'll put him down. He doesn't like the bright lights. So we'll put him down there. Now, you're going to pick a door. So let's say you pick door number 1. Now, Monty-Hall, your game show host, will reveal one of the booby prizes. So let's say door number 3. So there's nothing behind door number 3. Okay, now you've left with a choice of 2 doors. And that's what Monty-Hall is going to do. He's going to say, do you want to stick with your original choice, or do you want to switch? Now you might be thinking, well, there's only 2 doors, it's 50-50, it makes no difference if I stick or switch. In fact, you are twice as likely to win if you change your mind. Now this is very strange, it's counterintuitive. This problem was famously posed in a 1990 edition of Parade magazine, and thousands of people wrote in saying it's 50-50. Even mathematicians wrote in saying it's 50-50. It's just counterintuitive. A quick appeal to intuition might be to imagine 100 doors. So I've got 100 doors, and I'm going to ask you to pick a number between 1 and 100. Then I'm going to open 98 of those doors, leaving the door you picked and one other door. Now, how likely were you to pick the right door to begin with? Do you think it's more likely to be behind your door or the other door that I left unopened? Now, with 3 doors, it becomes a bit more counterintuitive. Here we go. There are 3 options. You can have the car behind the first door, and a goat behind the second door, a goat behind the third door. In the second case, you could have goat, car, goat, and in the third case, you'd have goat, goat, car. So let's say you pick door number 1, and in the first case, if you stick with door number 1, you're going to win. So let's put a tick next to that. And Monty-Hall, he's going to open, say, door number 3 or door number 2 to reveal the booby prize, and if you switch and change your mind, you're going to lose. So we'll put an X there. But in the second case, if I stick with door number 1, I'm going to lose. So let's put an X next to that. And Monty-Hall, well, he has to open door number 3. He's forced to open door number 3. Receives the car behind. So if you change your mind, you're going to win the car. So let's put a tick next to that. And in the third case, if you stick with door number 1, you're going to lose. So we'll put an X there. And if you change your mind, you're going to win the car. So we'll put a tick there. And as you can see, if you stick with your original choice, you win 1 out of 3 times. If you change your mind, you will win 2 out of 3 times. So the reason this fools you is because it's not genuinely random. If it was genuinely random, it would look something like this. Monty-Hall would open, say, door number 3 without knowing what's behind it. So he might accidentally reveal the car. If he opens door number 3 and reveals a goat, that means we're not in that third case, so we can get rid of those, and that's what we're left. And as you can see, it becomes 50-50 if you change your mind or not. This is how the modern equivalent of deal or no deal would work.
Right, now you can put your college education to practical work. Make sure you all get on a game show. But that is an example of what we're talking about, isn't it? How is it, let me pose that as a question instead of being rhetorical. How is that an example of what we've been talking about today?
Because he's giving you a chance to change your choice after he revealed that one door doesn't have the prize.
Your probability, your prior probability, you can update it, can't you? Make it a posterior probability because you have extra information. You know he deliberately, now this is the subtle part here, I don't know if you caught it at the end. The reason you have more information is because Monty Hall deliberately picked the door with the goat behind it. It wasn't random. If he would have randomly picked one of the two remaining doors, you'd had no advantage. It would be 50-50. And of course, occasionally he would reveal the car. But because he deliberately revealed the door with the goat behind it, you have additional information. And you can actually, I haven't found, didn't use that video, but there's some that actually take you through the Bayes formula, update your probability, and you see that it's higher than if you switch, because you have additional information. So posterior probability is revised based on what you know. All right. Have a great weekend. I will see you Monday refreshed, smiling, right?